Second speaker is Bob Lubarsky from FAU. He's going to talk about context-dependent deterministic parallel feedback Turing computability.
Thank you, Michael. I thought that my talk was going to be so exotic in a set theory symposium where all large cardinals and determinacy sorts of things, and I was going to be talking about computability. Turns out I'm just one among many talking about computability. Thank you for showing up for yet another computability talk. So I guess I should tell you what all of that means, building up a little bit at a time here. I will assume that you by and large know what Turing computability is. So let me tell you about feedback. The context that I want you to be thinking about is oracle computability, some sort of oracle computation. I will be specializing to Turing computability later on, and so you're invited to use that as your model even from the get-go, but at least for the beginning that's not even necessary. All that I have is some notion of computation that allows for an oracle. So, that much being said, what kind of oracle would one typically have? What's your typical, easiest oracle that you could think of? Don't answer, because the last time I asked, somebody said the empty set, which is not the answer I wanted. No, but the second answer I got was the right one, and that is the set of halting computations. Okay, so the halting problem is the oracle. If you do that, realize that the computations in the oracle are different from the computations that are calling the oracle. Because you see, the computations that are calling the oracle are calling an oracle, and the computations in the oracle aren't. So, they're different. What if they were the same? What if the oracle gave you some con and divergence information about some set of computations, and what you get when you ran the computations with that oracle was the same thing? Is this even consistent? We could ask that, but let's look at what that would happen. Suppose that x were a function from this set of computations, which I'll call omega, a partial function, and it gave you con and divergence information, and if you ran an oracle, if you ran a computation with that oracle, it would converge if and only if that's just what the oracle said it would do, and similarly would diverge if and only if that's what the oracle said it would do. So how could we model something like this? Well, realize that what we're talking about is some kind of fixed point. Because you see, given any x, even if this didn't happen, given any x, you could then say, well, what con and diverges when you use that as the oracle? And so what we're looking for is a fixed point. So if any fixed point will do, then realize there are many different possible semantics that you could have for this. Any fixed point would give you a semantics. What's nice about viewing this as a fixed point is it gives you an idea as to how you could actually show that there is such a set like this. If you're going to go for a fixed point, then the first thing that comes to my mind is let's try to find a least fixed point. And that's the semantics that I want to take. Such an x is a fixed point. Let's examine the least fixed point. So why even is there such a least fixed point? Well, how could you generate something like this? Well, consider a computation that just by coincidence doesn't call the oracle. This happens. That will either converge or diverge, and then you could throw that information into the oracle. That will never change. Now that we know what those computations do, you could then get an unambiguous answer for computations that call only the ones that we already have an unambiguous answer for. And you just keep throwing in this unambiguous con and divergence information until it closes off. And that's going to be your least fixed point. Let me show you another way that we can generate the least fixed point. So suppose you have your computation. So here's E. There's your computation you're trying to run. As it's running, makes a couple of steps. Then presumably it makes an oracle call at some point. I'm going to write that over here. I'm going to try to figure out what the right answer for the oracle should be. But I don't want you to think of the oracle like an oracle like the Greek oracle of Delphi or whatnot, which is all-wise and all-knowing and always has the right answer. You should think of the oracle more like the Wizard of Oz. So he doesn't really know what's going on. He has to do the scratch work in the background to figure out what the right answer is going to be. And I'm not saying that this tree is in any sense computable. This is just the scratch work the oracle is doing. So E makes an oracle call. The oracle runs this computation. Maybe this diverges. Okay, so it could well take more than omega many steps to see what's going on over here. Runs this for omega many steps. This doesn't make an oracle call. Diverges. That divergence answer gets reported back up to E. So E runs for a couple more steps and then makes another oracle call. Well, maybe this guy makes an oracle call, gets an answer, keeps on running, makes another oracle call, makes yet another oracle call. If this guy makes infinitely many oracle calls, then we see this fellow diverges. That gets reported back up here. And in this way, you can come to either E will stop after finitely many steps, and then it converges, has an output, and then it's over. Maybe E diverges, whatever. Okay, so this is what we can call the tree of subcomputations. And this will tell you whether such a feedback computation converges, diverges, what the answer is going to be. Now, you're all so polite. None of you has asked the question that I know you're all thinking. What about this self-reference over here? I mean, isn't this going to blow up somehow? After all, you can have a computation which then asks the oracle whether it itself and then whatever answer you get, you do the opposite. So how am I going to deal with this semantics? Well, one way of doing this is by looking at the tree of subcomputations. What's going to happen? So here's E. The first thing it does is it makes an oracle call. Okay? So the oracle now has to run this to see what the answer should be that the oracle returns. So when the oracle then, the E is calling itself, so the oracle runs this, and the first thing that happens is it makes an oracle call. And then when the oracle goes to run this, the first thing that happens is it makes an oracle call, and it's turtles all the way down. So the difference is between whether the tree of subcomputations is well-founded or not. In the case that I sketched over there, the tree is well-founded, and this will give you an unambiguous semantics, which you can prove inductively on the well-founded tree. In this case, this is an especially simple case here. This tree is is it a tree? Whatever. It's ill-founded, whatever it is. And so in a case like this, we would say that this computation is freezing. Because you see, E asked the oracle a question. The oracle figured all of this out, doesn't know what the right answer is, and so can't give an answer back to this. This computation can't continue. The standard model for a Turing oracle computation is you ask the oracle whether some natural number n is in the set or not. The next step, the answer appears on the tape, either 0 or 1, and the computation continues. Well, if there's no answer that can appear on the tape, there is no next step, there is nothing to do. So a computation like this freezes. That's why x is a partial function. It's a function from a subset of omega. There will be those cases in which x doesn't know what to do. And this is how you can avoid contradiction and avoid paradox. So, okay, what do you get this way? What do you get if you do feedback computability? Well, the relevant theorem here is that, I guess I can't call it x. Let me say y is feedback computable if and only if y is hyper-arithmetic, which probably means something to some of you, but not everybody. What can you do? If and only if y is a member of L omega 1 ck, where omega 1 ck is the least non-computable ordinal. And L omega 1 ck is the smallest admissible set. This really isn't a surprise if you're familiar with this theory at all, with some of the other things that I said. You can get the oracle I'm talking about is a least fixed point. Well, least fixed points of sufficiently simple positive inductive definitions, that closes off at the least non-computable ordinal. Admissible sets are exactly what you need to have to get least fixed points of inductive definitions. Another way of not being surprised at this result is that the semantics is based on whether a certain, not all that difficult to compute partial order is well-founded or not. Again, this is another aspect of admissibility. An admissible set is exactly where you have to be in order to be able to tell whether a partial order in that admissible set is well-founded or not.
It can be well-founded from the inside. It's not really well-founded.
Oh, well, yeah. I was being a little sloppy, yes. So I will refer to this later, so this is a good moment to bring it up. If A is an admissible set, of which L omega 1 ck is an example, then for P in a partial order, standard, okay, I'm looking at standard, epsilon standard admissible sets, so well-founded admissible sets. Then for a partial order to be well-founded, P is well-founded if and only if there is in A and, a rank function, an order preserving homomorphism from the partial order to the ordinals of A. So if something is well-founded, there's a witness because you can assign ordinal ranks to the members of the partial order. If something is not well-founded, it doesn't mean there's going to be a witness to that. You won't necessarily be able to find an infinite descending sequence. You won't necessarily be able to separate the well-founded part from the non-well-founded part and see that the non-well-founded part has no least element. So this allows for the possibility of non-standard models making mistakes about these things. If you want a witness to the non-well-foundedness of a partial order, you might have to look at definitions over the admissible set as opposed to witnesses within the admissible set. Is that good enough? Good.
Well,
Yeah?
one point of clarification.
Please.
Your oracles could be partial functions, right?
Yeah.
And in case you make a call to a partial function, it means computation that didn't stop.
It freezes. If you make an oracle call to something which isn't in the domain, then the oracle doesn't have an answer to give. So there is no next step in the computation. The next step would be the answer, but if there's no answer, there's no possible next step. So that's what I call freezing. Is that okay? Good. Okay, so I guess that's enough about feedback for the moment. Let me point out, in case somebody's wondering, this whole thing relativizes. You could have started with some other oracle, not to be confused with the feedback oracle, and then you would get that X is feedback computable relative to an oracle O, a fixed oracle O, if and only if Y is hyperarithmetic in that other oracle O. So the whole shebang relativizes. Okay, well, if that's feedback, then let's talk about parallelism. Let me just briefly make the case for parallelism in computer science. It's an important concept. You could understand, for instance, the distinction between P and NP, as NP is a parallel version of P. Non-deterministic polynomial is like running exponentially many polynomial algorithms in parallel. Parallelism also comes up, or can be viewed in quantum computation, where you're trying to take advantage of superposition of states in order to run many algorithms in parallel. It also comes up with distributed computing. If you have, lots of computations now are done in a distributed fashion. Maybe some big scientific computation is taking advantage of the rest time that, when a user is not using a computer to do some big computation, and then answers can come back to the central processor in some sort of random order, and this can have an effect on the outcome. So parallelism is an important topic in computer science. My experience is that it's not so important in mathematical logic. I don't hear computability theorists talk about parallelism an awful lot. And I think the reason for that is that it can be simulated by a sequential computation. If you just consider regular Turing computability, then you can run all of the possible Turing computations sort of in parallel by sort of simulating it sequentially. By dovetailing the various computations, you can run them all, but it's just a sequential computation. So there isn't really any parallelism that happens that can't be sequentialized in regular Turing computability theory. In this context, however, something different is going on. Because you see, if you have a freezing computation, you better not make an oracle call about it. So if you have some index E, let me call this one E hat, you may want to know, well, for various arguments, do I get convergence for some argument n that I might put in here? And you might try to do this by dovetailing. Regular Turing computability, you just dovetail over all possible n's until one converges, But that's not going to work over here, because you see, if you start, so by dovetailing, you do a couple of steps in E hat of 0, and then a couple of steps in E hat 1, and then go back to E hat and 0. If this computation at some point makes an oracle call, and it happens to be a freezing oracle call, game's up. The computation stops at that point, and even if E hat of 1 converged, you'd never find that out because the computation is frozen over here. So there really is a notion of parallelism which is non-trivial, and it gets you something new. So I better tell you what the semantics of parallelism is. So how's this going to be? Let's see. So we have a computation here. I'm going to draw a tree, but it's a very different kind of tree from the tree of subcomputations. So E, then it runs a couple of steps over here, and eventually it makes a parallel oracle call. I'll call that F. So in order to make sense of this, imagine that you're going up L. Okay, we're working in L, you're going up the L hierarchy, and some of these computations converge, some diverge, some maybe freeze or whatnot. As you're going up L, you find out. So inductively, we have some sense as to whether some of those converge or not. If you're at L omega, maybe you don't see that any of these con or diverge. You've no information yet. L omega squared, you don't see anything. Eventually, you happen to see, oh, okay, F of 9 equals 64. Okay, perhaps that shows up at some stage in L. So now E continues. This is an answer, a possible answer that E got back from its parallel call. So at this node, E continues computing, does a couple more things. Maybe another parallel oracle call is made at this point. So here we get a parallel oracle call of G. And maybe once this oracle call is made, it could be that see, we're already at some L alpha where we saw this fact. Maybe that L alpha already has figured out some G facts. So maybe at that, so you can immediately write down G of 14 is something, and maybe you had several G facts. G of 19 diverges. We may have seen a bunch of things. Okay? But then these continue and they make oracle calls. You don't see anything. Okay, in L alpha, we don't know what the new oracle calls that these computations make go on. So okay, so you go up L some more, and then we find out a bit later, wait a minute, F converged not only on 9, F also converged on 68. And we saw that this was 3 or whatnot. So if you're going to get a deterministic model over here, then at some point you're going to have to decide which answer do I want to use. Because you see, if you accept this as your answer to the parallel oracle call, then maybe you find out the value is 7. If you accept this as the answer, you get a different computation. The computation will go differently from this point. Eventually you're going to have to decide which answer you want to accept. And you do that the first time you see your computation coming to a value. So you keep on going up L, and eventually maybe get another oracle call over here. This asks about H. And you see that H of 96 diverges, and then the computation continues, and then it enters into a halting state. This may be the first time you see a halting state in this tree over here. That's what you're going to pick. That's the answer you're going to pick. So you see, this is not a tree of subcomputations. This is the tree of possible runs. Any of these answers is acceptable as a parallel oracle call. So there's one run of F that would go down this branch and one that goes down this branch, and there could be plenty other branches that happen. As soon as you see your top computation ending, that's when you stop. How could the top computation end? Well, one way is it makes finitely many oracle calls, and then after it stops asking questions, it enters into a halting state. So that's one way that this computation could end. Another way it could end is after finitely many steps. It asks this question, it gets this answer, and then it takes omega many more steps and makes no more oracle calls, but you see that the E computation diverges. So this would be a terminal node on the tree at this point, because no more oracle calls are made, but the computation could be seen to diverge at that point. The final way that you can come up with a value for E is makes an oracle call, which makes an oracle call, which makes an oracle call, which makes an oracle call all the way down. As soon as you see that this tree is ill-founded, then you know that E has diverged. So those are the three ways that you can get a value for E. I'll summarize this. When filling in the tree of runs, E can be given a value by either one possible run halts, one possible run diverges, and 3, which is kind of like a subcase of 2, the tree becomes ill-founded. So you go up L, and as you're going up L, some computations converge and some trees become ill-founded, and that's the semantics for these parallel oracle computations.
What do output if what do output if in the first case?
In the first case, well, E enters into a halting state, and whatever's on the output tape is the output.
But couldn't it be the third case and the first case at the same time? On one line it arrives at a halting state, and on the other one it goes down forever.
That's not possible, actually. There is a real concern that you're bringing up. That particular thing is not possible because the Turing machine will enter into a halting state at a successor stage, whereas a tree can only become, oh, no, that's not completely true. This can also happen at a successor stage. If at the very high ordinal you get an answer for one oracle call, and then the future oracle calls all gave you answers at lower ordinals. So, but even more concretely, you could enter into more than one possible halting state at the same time, depending upon which oracle answer you got. If you went this way, you have one halting state. If you go this way, another halting state. So it is a real concern. I say somewhat arbitrarily and somewhat unsatisfactorily, pick the leftmost one. Make some arbitrary decision among all the possibilities. Take the leftmost branch that ends you into one of these three situations, if more than one happens at the same time. And I take that as your answer. Good enough? Okay, now that we have this, I can actually tell you why this is a context-dependent semantics over here. Because you see, why would we say the actual run we use goes this way instead of this way? Not because f of 9 is 64, but because of what E does with that information afterwards. If E asks some amazingly ridiculous oracle call from this point on, this isn't going to do anything. This branch will not be fruitful. We will come to our final conclusion down this branch, perhaps. Whereas a different computation, making the same oracle call, might do something very different with the information that it gets back and ultimately decide, this is the branch I want to go down. So that's why it's context dependent. I will mention in passing, this is one possible semantics. There are other possible semantics that you can give. I want to talk about this because this gets you something different from omega 1ck that we had over there, and I can tell you what this gets you. So that's what I want to talk about, this particular semantics. Is there anything more I should say about that right now? I will take that as a no. What does this get you? Well, no big surprise, it's going to be some initial segment of L. Let me tell you which. This definition, please bear with me. It took me a while to get used to it. What can I tell you? This is what it is. We say that an ordinal alpha is pi 1 gap reflecting unadmissibles kind of a wordy name. If you have a better suggestion, let me know. If for all pi 1 formulas, which implicitly is allowed to have a parameter or parameters from alpha, but one free variable, if in L alpha plus, this means the next admissible beyond alpha. If in L alpha plus, this pi 1 formula is true with parameter alpha, using alpha as a parameter, then here comes the reflection. There is some smaller ordinal such that in L beta plus, the same formula is true where you also need to reflect the parameter. This is why the notion's not trivial. If you have a pi 1 formula in a structure and you go to a smaller structure, the pi 1 formula is still true. So that's trivial. This is not that trivial because the parameter itself is changing. One parameter is changing. The other parameters are fixed. This parameter is changing. Yeah, let me try to convince you that there is something natural about this. I'll put up a name over here. Let gamma be the least such ordinal. Gamma has many other characterizations.
What do you mean such?
The least pi 1 gap reflecting on admissibles ordinal. That's why I didn't want to rewrite the whole. I'd rather say such. Okay, so gamma has other characterizations, or pi 1 gap reflection also has other characterizations. Gamma, let's see, so sigma 2 determinacy, sigma 0 2 determinacy. Winning strategies for sigma 0 2 games for one player or the other. Gamma is the least ordinal, where such winning strategies are either in L gamma or definable over L gamma. The winning strategies for the positive player, for player 1, will always be a member of L gamma. A winning strategy for player 2 might not be in L gamma, would only be at first definable over L gamma. And this is the first such, the first ordinal where such properties appear. Gamma is also the least ordinal that satisfies sigma 1 1 reflection. In this case, the superscript 1 refers to second order logic. Second order logic. So this is saying that if you have some formula true in L gamma, where you have a set quantifier, quantifying over all subsets of L gamma, then that will reflect to some smaller initial segment of the L hierarchy. It's also the first closure point of sigma 1 1 monotonic inductive definitions. So I was talking before about L omega 1 ck being where you have at least fixed points of sufficiently simply defined positive inductive definitions. Well, if the definition of the inductive definition gets sufficiently complicated, you can go beyond L omega 1 ck. Oh, in this case over here, this refers to arithmetic. This is not second order, well, it's sort of second order logic. This just refers to second order arithmetic. So L gamma is the first place where such inductive definitions close off. And the final equivalence that I'll give, this is the least place where you get the definability of sets of integers that are sigma 2 definable in the mu calculus. So what's the mu calculus? The mu calculus is a fragment of second order logic where you have the regular first order part, but you're also allowed to have set terms that you can refer to by least and greatest fixed points. So if you take that language, so you can and interpret that in arithmetic. So you can talk about the least fixed point given by some arithmetic definition, and also talk about the greatest fixed point given by some arithmetic definition. And even more than that, the least fixed point can be defined in terms of some greatest fixed point, which itself depends on the least fixed point that you're defining. There's a certain feedback that's built into the language of the mu calculus. So by sigma 2 over here, I mean the definition of a set term, which is defined using some least fixed point x, which is defined in terms of some greatest fixed point y, and x and y can sort of depend on each other in a certain way. So this is what I mean by sigma 2, least fixed point followed by a greatest fixed point. Such sets that are so definable are sigma 1 definable over this L gamma. So I would hope that seeing all of these equivalences for L gamma might go some way to convincing you that it is indeed a fairly natural ordinal. I can even say more by way of trying to convince you that it's a natural enough thing to look at. Let's consider the dual notion. Some of those notions dualize, whoops, some do not. So for instance, you might first think with the dual of sigma 0 2 determinacy would be pi 0 2 determinacy, but that's not anything different. So that's like a self-dual property. The dual of sigma 1 1 reflection makes perfect sense. So we're talking about pi 1 1 reflection, which is different from sigma 1 1 reflection and happens at a different place. The least, the closure point of sigma 1 1 monotonic inductive definitions, well, that dual would be the closure point of pi 1 1 monotonic inductive definitions, and that's also different, but the same as this. So if you get pi 1 1 monotonic inductive definitions, these end up being equivalent, give you the same ordinal. The dual to sigma 2 definable in mu calculus would be pi 2, but that's just complement. This is a set theoretic complement. So whereas this is sigma 1 definable over L gamma, the pi 2 definable sets in the mu calculus would be pi 1 definable over L gamma. That's nothing different. What's the dual of gap reflection? The dual to gap reflection is to say that alpha is alpha plus stable, which is just saying that L alpha is a sigma 1 substructure of L alpha plus. I guess I should point over here that, well, no, let me drop that. So, yeah, you see, you kind of lose the parameter. With gap reflection, this parameter gets reflected because you're talking about pi 1 formulas. When you have a sigma 1 formula, you can actually absorb the parameter into the sigma 1 definition. So this ends up being, see, this is fairly natural. This doesn't look so bad over here. These seem like the same level of complexity. This, the dual to pi 1 gap reflection actually becomes much simpler. And so this looks like a fairly natural notion. This ends up being weaker. This is strictly weaker than what I have on the other board. And so when you look at these properties over here and you dualize it, well, it turns up that this is the right property that you get, and you end up getting something strictly stronger. So, okay, and then the theorem in question, of course, is that...
But you do not mean that these notions coincide, or what are you...
Yeah, these do.
Pi 1 monotone inductive definitions is just the closure ordinal is omega 1 ck.
I don't think so, or maybe I'm misremembering the, maybe it's not monotonic. Maybe I should drop the monotonic.
Drop the monotonic.
Yeah, okay, that's
Okay.
a difference.
Maybe I should have dropped the monotonic here. My apologies if I misremember that. Is this okay now?
Sigma 1, 1, it makes no difference. But pi 1, 1, it does make a difference.
Okay. Great, thanks. So the theorem in question is that the set X is parallel computable. I won't repeat the whole thing. It's parallel computable if and only if it's in L gamma. This is what you need in order for that semantics to close off. So, sometimes people say that in a talk you should prove something. Sometimes people say in a talk you shouldn't prove anything. So I'm going to try to compromise over here a little bit, and I will show you the basic idea for one direction. I'll just do one direction, the easier direction over here, and maybe it'll bring some ideas together over here. So what will I show? I will show that any parallel computation closes off before gamma. Now, if it freezes, then you may have to go all the way up to gamma to see this, but if it either converges or diverges, you'll find out by gamma. Okay, so why is this true? Well, there are the ordinals, okay. Here's gamma. Suppose you had some computation which only terminated at some larger delta. Now, suppose it's that E over there. Suppose that terminated at some delta larger than gamma. How could that have happened? Well, the only reason there was any delay in seeing what was happening with this computation were because we were waiting as we were going up L to get the answers to various oracle calls. The only other thing that's happening is you're doing a Turing computation, and that's easy. That's just, finitely or omega many steps. So why did we have to wait until delta in order to see what was happening over here? Well, I guess this thing also happened at some stage between gamma and delta. Okay, why did we have to wait past gamma? Because we were waiting for this to happen. So there might have been some other computation, perhaps not that E, which converged, diverged, did whatever it was going to do at this step over here. So you do this finitely many times, and you finally see, oh, well, there was some computation for which we got an answer only at gamma. So it suffices for me to show you that nothing new is going to happen at stage gamma. Suffices to show no new con or divergence at L gamma. Okay, so why is that the case? Well, if we get anything new happening at L gamma, it's because of one of these three cases. How could a new computation be seen to halt at stage gamma? Well, something halts at a successor stage. Okay, you went up a little bit, you saw some tree or other converge, you got some answer over here. Gamma is not a successor ordinal. You're not going to see something coming to a halt at stage gamma. Okay, well, maybe we didn't make an oracle call, a new oracle call, but we saw that some Turing computation diverged. That, just you ran something and it diverged. Gamma is not of the form alpha plus omega. Okay, gamma is a limit. It's not just a limit, it's a limit of limits. No Turing computation is going to diverge at stage gamma. The one which is most powerful, the one that you have to worry about, is the tree. We could see the tree became well-founded, that we didn't see it before. So we're going up L, we're getting answers, more answers to our oracle calls. At stage gamma is the fear. You see, oh, here's this divergent run. I'm going to call this computation divergent, but I didn't see that before. All the other trees we had were well-founded. Okay, so how do you express that? In order, so let's see. So this comes down to part 3. The tree of runs T gamma is ill-founded, but the tree of runs T alpha for all alpha less than gamma is well-founded. Okay, how do you say that something, a tree, is well-founded when you're at an admissible set? This is a sigma 1 assertion. There is a rank function. If a tree is well-founded, there is a rank function into the ordinals of that set. This is a sigma 1 assertion. So, how do you say that this tree is ill-founded? You say it's not well-founded. This is a pi 1 assertion which uses the ordinal gamma as a parameter. To build a tree of runs, everything else is very simple. It's very straightforward. So if we get divergence happening because of case 3, then what would that be? Well, so case 3, to say that T gamma is ill-founded, this is pi 1 in any admissible set containing T gamma as a member. Well, T gamma is easily enough definable over L gamma, and therefore this is a statement in L gamma plus. Now you use the pi 1 gap reflection to get that the same statement of ill-foundedness was true at some earlier stage. By gap reflection, for some smaller beta less than gamma, T beta plus thinks that T beta is ill-founded. Well, this is exactly what admissibility will do for you. If this
beta plus. No.
Oh yeah, oh thank you. Thank you, yes. If this admissible set thinks that this tree is ill-founded, it really is ill-founded, and so we saw the divergence of this computation at stage beta already before gamma. So this shows that nothing new happens at stage gamma, and that's why gamma is an upper bound for the strength of this kind of computability. In order to complete the theorem, which I'm not going to do, don't worry, you have to show the other direction. You'd have to show how you could actually, in a parallel fashion, this parallel feedback fashion, build up all of the initial segments of L gamma. So, okay. Whoops. Guess I'll have to, oh, just break it. So, I actually proved something for you, and that was my goal, and so this is a nice place to stop.
Plenty of time for questions. Any questions?
Was I that clear?
So let me ask you, so in a certain sense, these notions are, well, they are maybe unusual, but in some sense they're also very natural. So has anybody else come up with this before? I mean, in the literature, is there any other places where people have looked at similar things?
That's a great question. No big surprise. I was wondering that myself. I guess I'm supposed to say that if there are such places in the literature, if somebody knows about them, I hope that you tell me. Probably the truth of the matter is I hope that you don't tell me, but that's another matter. I really don't know of any. I mean, it's a good question. This is not based on anything, okay? I mean, Turing almost could have done this himself. That would have been a bit of a stretch. But this has the flavor of the higher recursion theory from a half century ago. So you'd think it might have been done then. Not only this, I even asked about this. I mean, forget the parallelism, but just feedback computability. I did, thinking, how could this not have been done before? I sent out a question on FOM, Foundations of Math Mailing List, and the answers I got, honestly, kind of showed me that nobody even really knew what I was talking about. But that's not completely true, because after the feedback paper was written, I happened to be going through Rogers' classic textbook on Turing Computability theory for a totally different purpose. And I saw feedback right there. There were 2 pages where he's exactly discussing feedback. Doesn't attribute it to anybody, includes no proofs. It's crazy because Rogers was like the basic book, for decades for computability theory. It's right there. It doesn't use the word, but it's right there in black and white. Nobody picked up on it. Nobody followed up on it. Even to the point when I asked about it, nobody could figure out what I was talking about. So, Rogers seemed to have understood feedback without knowing freezing. He didn't figure out freezing, but he knew that it would get you up to omega 1 ck. And that's all I could find for prior history for this.
But
Yeah.
I mean, we discussed this before. I mean, the very right-hand board, not the parallelism. I mean, this is an example of what Kleene did in the late 50s and early 60s. Just the right-hand board, just what you're calling feedback. Right? This is an example of Kleene recursion in type 2 objects.
Well,
I mean, when he formulated his papers, I mean, he did this in terms of this equational calculus, but then he published a couple of papers where he tried to bring in the Turing machine model to try and give some kind of equivalences. So he does what amount to the feedback computation thing, the type 2 object and the jump operator, explicitly using Turing machines. It's true that probably many people didn't read this paper. What? To parapet. One is in the TMS, and then the second one is in the CLNPS for the Stanford volume. But I think you have to say that the feedback stuff is an example of Kleene. The parallelism I've not seen.
okay, well, give credit where credit is due. I mean, sure, Kleene did look at things that were a lot like this. And if you're talking about admissibility and L omega 1 ck and so on, there have been enough different formulations of this that it would be a surprise if you couldn't find anything in prior formulations that had characteristics similar to what I presented over here. Whether you want to say it's the same thing or something different, I don't know. There is this notion of freezing, and I'll point that over here. This is, perhaps another disagreement between Philip and me. Philip likes to point out that freezing could be viewed as a certain kind of divergence. And that's true. I mean, if a computation freezes and you don't get an answer, isn't this just divergence, perhaps some higher kind of divergence? And yeah, I mean, you could look at it this way, and you could see what you get when you do that. I think that if you don't account for freezing as a different phenomenon, that you're missing something. That there are things you can get to by taking freezing seriously that you'll just miss if you look at it as pure divergence. I mean, Philip might disagree with this, so I don't want to come down hard on this one way or the other. And that's what seems to be new in this way of looking at feedback, is my opinion.
Well, since I seem to be halfway between you and Philip, let me mention that if you want to make again, nothing about the parallelism, just the feedback part. If you want to make this look like Kleene type 2 recursion, then I think it should be recursion in the specific object 2E. And furthermore, the freezing here, I think, corresponds to divergence in Kleene.
Yes.
And divergence here corresponds to a particular value, which I forget whether it was 0 or 1, but it's an actual value in the Kleene picture. So I think there is a correspondence, but for example, you're absolutely right that you have to distinguish freezing, what you call freezing, from what you call divergence. But unfortunately, the terminology seems to be that Kleene calls the former divergence.
But there are two values here. There's the up arrow and the down arrow.
There are two values,
And
halt
0,
and
1.
don't halt. And of course, here there's the additional thing that there are values besides just whether it halts or not. But I think that can be smuggled into the Kleene picture without too much difficulty. But anyway, the translation, I think, should exist, but it involves actually changing the terminology in at least one place.
Two more questions. Yep.
Okay, so if I remember correctly, that this feedback idea first showed up not in the context of Turing machines, but for infinite time Turing machines, right?
The first time the feedback showed up as such was in the context of infinite time Turing machines, interestingly enough. Turing machines are simpler than infinite time Turing machines, but for some reason that's where it first appeared. So to emphasize that whether or not this is really Kleene-esque or not, if you look at it this way, you can substitute in any notion of oracle computation and get some notion of feedback, and you also don't have to take the least fixed point semantics or other semantics you could look at. Or that wasn't your question.
No, that was it. So my question is now, have you considered stronger models than ITTM computations, like alpha Turing machines or ordinal Turing machines, and looked what happens when you feedback them?
I haven't gotten that far yet. Of course, it's one of the next things on the docket. I was in particular, I was interested in the feedback e-recursion. Looking at sets. It's a great
recursion on sets.
Sets, yeah. Yeah, I mean, it could be that maybe the notion in some cases just doesn't make any sense. Maybe it's not coherent. I don't know, but all these things deserve looking at, I would say.
Well, I mean, of your title, what I'm missing is where is the deterministic parallel picture?
Thank you. The way I gave the semantics for this over here is I said, pick the least, in the sense of L, path, which gives you an answer, be it convergence, divergence, whatever. That's what makes it deterministic. What if you allowed all possible paths that gave you an answer? That would be non-deterministic. And that's, interestingly, I wasn't able to see exactly what you got for that. By similar arguments about L gamma, you can show that any non-deterministic computation that halts will halt before stage gamma. But whether you can actually go up that high is another matter. That may seem paradoxical because with non-deterministic computation, it looks like you get more. There are more possible answers. But that's just what screws you up, because it's too flabby. You can't look at a computation and say, does this give me a well-founded model of some, theory or other, some, L alpha? Because by one run of that computation it will, and by another one it won't. Because suppose you have a computation that agrees with everything. It says yes to everything. So is this sentence in your term model you're trying to build? Yes. Is this sentence not in the term model you're trying to build? Yes. And so there's a run, pick anything you want, some run of that computation will give it to you. So you can't rely on these things, and this is what stops you from being able to actually build your term models for the L alphas as alpha runs through gamma. So I don't know what you get if you
So you are coming to the paradoxical conclusion for computer science that deterministic machines are much stronger in power than parallel.
I can't say that because maybe it does get you all of L gamma. I don't know. But it's easier to analyze. Is that paradoxical?
No. It's of the same flavor of the talk before where it was shown that many simple computation are in some respect very hard, so now we are getting the opposite. Some hard computation are simple. Then,
Yeah, well, logicians love paradox.
That's great. So all questions are open, so let's thank him again.